Not okay.
What?
What is Burr?
Oh!
You can think about that.
Right? It makes sense. It makes sense.
You can think about that. Yes.
We should go class ski trip.
Class
To
ski
snow
trip?
trails.
That would be
Or tubing.
epic.
Go tubing.
That would be epic. If there was a way to plan that, I would. If there was a way to plan that, I would. I think we have a ski club, don't we?
We do.
We do. So today, our goal is to wrap up the majority of the notes for the chapter. Our next test is next Friday. This is a very short chapter. So, I know that you guys were thinking, man, I want to have a test 2 weeks in a row. Well, I can do that. So, I did that just for you guys. So, but this chapter is real easy. This will be one of the easiest tests that you guys should take of the year. So,
Oh my gosh.
we're going to start out today with the Maxwell-Boltzman distribution.
Is this the same dude who like normally?
Who what?
Is this someone con?
This is Khan Academy. So all you have to do is sit back and relax and enjoy this for the first 9 minutes of class today. No, don't write anything down. I'm going to summarize it up after we watch this.
And then the distribution, and this right over here, this is a picture of James Clerk Maxwell. I really like this picture. It's with his wife, Catherine Maxwell. I guess this is their dog. And James Maxwell, he is a titan of physics, famous for Maxwell's equations. He also did some of the foundational work on color photography, and he was involved in thinking about, well, what's the distribution of speeds of air particles, of idealized gas particles. And this gentleman over here, this is Ludwig Boltzmann, and he's considered the father, or one of the founding fathers of statistical mechanics. And together, through the Maxwell-Boltzmann distribution, they didn't collaborate, but they independently came to the same distribution. They were able to describe, well, what's the distribution of the speeds of air particles? So let's back up a little bit, or let's just do a little bit of a thought experiment. So let's say that I have a container here. Let's say that I have a container here, and let's say it has air. And air is actually made up mostly of nitrogen. Let's just say it has only nitrogen in it, just to simplify things. So let me just draw some nitrogen molecules in there. And let's say that I have a thermometer. I put a thermometer in there, and the thermometer, it reads a temperature of 300 Kelvin. What does this temperature of 300 Kelvin mean? Well, in our everyday life,
What does that mean?
The average kinetic energy.
Yes, the average kinetic energy. You guys ever think about what the average kinetic energy means?
Temperature?
Do you ever think about words?
Dog.
No.
You know that kinetic energy is movement, right?
Some below and some above.
Yes. Average means some below and some above.
we have a kind of a visceral sense of temperature. Hey, I don't want to touch something that's hot. It's going to burn me. Or that cold thing, it's going to make me shiver. And that's how our brain processes this thing called temperature. But what's actually going on at a molecular scale? Well, temperature, one way to think about temperature, this would be a very accurate way to think about temperature, is that I'm spelling it wrong, temperature is proportional to average kinetic energy of the molecules in that system. So let me write it this way. Temperature is proportional to average kinetic energy. Average kinetic energy in the system. That's right, average kinetic energy. So let's make that a little bit more concrete. So let's say that I have two containers. So it's one container, and two containers right over here. And let's say they have the same number of molecules of nitrogen gas, and I'm just going to draw 10 here. This obviously is not realistic. You'd have many, many more molecules. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's say we know that the temperature here is 300 Kelvin, and the temperature of this system is 300 Kelvin, and the temperature of this system is 200 Kelvin. So if I wanted to visualize what these molecules are doing, they're all moving around, they're bumping, they don't all move together in unison. The average kinetic energy of the molecules in this system is going to be higher. And so maybe you have this molecule is moving in that direction So that's its velocity. This one has this velocity. This one's going there. This one might not be moving much at all. This one might be going really fast that way. This one might be going super fast that way. This is doing that. This is doing that. This is doing that. So if you were to now compare it to this system you could still have a molecule that is going really fast. Maybe this molecule is going faster than any of the molecules over here, but on average the molecules here have a lower kinetic energy. So this one maybe is doing this. I'm going to see if I can draw on average. They're going to have a lower kinetic energy. That doesn't mean all of these molecules are necessarily slower than all of these molecules or have lower kinetic energy than all of these molecules, but on average, they are going to have less kinetic energy. And we can actually draw a distribution. And this distribution, that is the Maxwell-Boltzman distribution. So
This is the most important thing. All right, this distribution, you are going to have to either draw or answer a question about on the AP test. I guarantee you. Every year it's on there. And we'll do this in months.
So if we, let me draw a little coordinate plane here. So let me draw a coordinate plane. So if on this axis I were to put speed, and on this axis I would put number of molecules. Number of molecules right over here. For this system, the system that is at 300 Kelvin, the distribution might look like this. So it might look, the distribution, let me just in a new color. So the distribution, this is going to be all of the molecules. The distribution might look like this. Might look like this. And this would actually be the Maxwell-Boltzman distribution for this system. For system, let's call this system A. System A, right over here. And this system that has a lower temperature, which means it also has a lower kinetic energy, the distribution of its particles.
What do you think it would look like?
Higher?
No, we know
it's
lower.
Dog.
So the most
More left. Left, I mean, no, or technically right, so it would look like this, because there will be more particles at a lower speed.
likely, the most probable, you're going to have the highest number of molecules at a slower speed. Let's say you're going to have it at this speed right over here. So its distribution might look something like this. Now, so it might look something like that. Now, why is this one? It might make sense to you that, okay, the most probable, the speed at which I have the most molecules, I get that that's going to be lower than the speed at which I have the most molecules in system A, because well, these, on average, these things have less kinetic energy. They're going to have less speed. But why is this peak higher? Well, you got to remember, we're talking about the same number of molecules. So if you have the same number of molecules, that means that the areas under these curves need to be the same. So if this one is narrower, it's going to be taller. And if I were to somehow...
He literally said that they both have like 10 molecules, so why is B higher when they have the same number of molecules, which is what the y-axis is measuring?
The area has to be the same. So, right? The area under the curve has to be the same. It's the same amount of particles. So if you push it together, right? You push it together.
Yeah.
You can only go to 0, right?
Yeah.
Because 0 Kelvin is absolute 0.
Yeah.
This is Kelvin temperature, right?
Okay.
For the speed. If you push it together and you have more particles, it's going to be a higher hump. Because those particles, as they get closer together, you have to have the same amount of area.
But
So my number of molecules isn't changing, but my number of molecules at a lower speed, right?
oh, I see.
Yes?
I see.
So it's the same number of molecules. There's 7 molecules under this hump, but they're more spread out because they're at a higher speed.
Okay.
Down here, because they're at a lower speed, they are getting more jammed together, so the hump has to go higher.
Okay. That's just so weird.
It is, which is why I'm doing this, and I'm going to do it again in the notes.
Okay.
All right, it takes a little bit of conceptual thinking. All right, it takes a little bit of conceptual thinking.
Is the temperature of this system even more? Let's say I create a third system, or I get this, or let's say I were to heat it up to 400 Kelvin. Well, then it would look, then my distribution would look something like this. So this is if I heated it up, heated up. And so this is all the Maxwell-Boltzman distribution is. I'm not giving you the more involved, hairy equation for it, but really the idea of what it is. And it's a pretty neat idea. And actually, when you actually think about the actual speeds of some of these particles, even in the air around you, you might say, oh, it looks pretty stationary to me. But it turns out in the air around you is mostly nitrogen, that the most probable speed of, if you picked a random nitrogen molecule around you right now, so the most probable speed, and I'm going to write this down because this is pretty mind-blowing. Most probable speed at room temperature. Probable speed of N2 at room temperature. Room temperature.
To what?
Temperature.
Bananas.
So let's say that this was the Maxwell-Boltzman distribution for nitrogen at room temperature. Let's say we call room temperature 300 Kelvin. This most probable speed right over here, the one where we have the most molecules, the one where we're going to have the most molecules at that speed. In fact, guess what that is going to be before I tell you, because it's actually mind-boggling. Well, it turns out that it is approximately 400 and actually at 300 Kelvin it's going to be 422 meters per second. 422 meters per second. Imagine something traveling 422 meters in a second.
Thank goodness they're light, right? Thank goodness they are light. Can you hit the lights, Joey?
Oh, that is an equation.
There is an equation, but you're not responsible for the equation. So that's good. Can you hit the lights, Joey?
Oh yeah, sure.
So let's just summarize what we just heard. So what are you responsible for knowing? Here's what you're responsible for knowing. Not the equation, you're right. So, come on, adjust. Okay. So we are talking about the Maxwell-Boltzman distribution. So this is the Maxwell-Boltzman distribution.
Is this chapter 5? No, it's part 2.
Yeah, part 2. Maxwell-Boltzman distribution. So let's start out with his container of air, right? And let's do, this was at 300, he drew a little thermometer, and he said that this was 300 Kelvin, right? And there were air particles in there. We have defined, since freshman year, temperature as the average kinetic energy of a substance. Temperature is the average kinetic energy of a substance, and we know from physics or freshman year how to solve for kinetic energy. What is the equation for kinetic energy? 0.5 mv squared, correct. 0.5 mv squared. You learned that in physics or freshman year. You should have at least. All right, 0.5 mv squared. So he was talking about those nitrogen molecules moving super fast. So yeah, crazy high velocity, but their mass is basically what? 0. That's why you don't feel them hitting you at 422 meters per second. So here was beaker A. So he drew, container A. Let's not say beaker. Here's container A. We're going to do 7 molecules. Let's do 6 actually. 2, 3, 4, 5, 6. So container A, this was at 300 Kelvin. So draw yourself some arrows. Try to make them some different than others. Here was container A. And then container B, what did he do to it? He cooled it off, right? So he made this second container 200 Kelvin, which means out of our 6 particles, it's really hard. I keep drawing this like a dice. Should have done 7. Now it looks like a smiley face. I did not mean that. That was an accident. I was not trying to draw a smiley face. These arrows, some could be longer than all the other ones. But in general, all these arrows, or more arrows than the other ones, need to be what? Shorter. More arrows need to be shorter. So that was container B. 6. And then in container C, we had 6, 2, 3, 4, 5. I cannot, I'm drawing like a pattern every time. Can you draw these more random than I am? Okay. Like, doesn't that look like a pattern?
strong they are.
Okay. This one was at 400 Kelvin. So the majority of these arrows are going to be longer than the first box, right? So we have container A, container B, and container C. Now, what you have to understand is this distribution. So on this graph, we had number of molecules on the y-axis, and we had speed on the x-axis. And then beaker A was kind of in the middle. So here was container, I don't want to say beaker. All right? Sealed container A. So here was the hump for container A. And then he asked you, what happens when you cool this down? Well, when you cool it down, B looks like this. It's going to be a higher hump and to the left. All right? So this is letter B. Y to the left and higher. Well, we know it has to be to the left because it's a lower speed. Agreed? Why does it have to be higher? Because the area of these two has to still be the same. So if I was just doing length times width, like underneath the curve, right? Yes? If I am moving my particles to the left, I'm scrunching them together, then my height has to be larger. Correct? Does that make sense? And don't overthink this, okay? What you guys have to know, lower temperature, higher to the left. Sorry, that was not for your view. Higher to the left. Lower temperature, higher to the left, because you're scrunching them up, right? Now, this other way, you could essentially go into infinity. The other way, right? Is there a maximum temperature that you can reach? No, there's not. But here, you've got absolute zero. So that's another way to think about it. They're going to scrunch up as they get closer, because they can't. Theoretically, we've never reached in real life, we've never reached absolute zero. We've got close. And then there's then you start going to quantum physics. And if you go below absolute zero, some people think it actually gets super hot. It's really interesting. Ask Mr. C about that. All right. And then if I heat it up, my hump is going to be lower and to the right. So here's hump C. Maybe I'll do this one with lines. All right. Hump C. Because now I have more particles at a higher speed, but because I have more particles at a higher speed, the hump has to go lower, right? Because it has to be the same area under the curve. Does that make sense? Yes. Yes? So, the question that you would have to answer, well, you probably just have to draw this, but let's just write it in here. So the question is, why is B higher? How would you answer that question? Not more particles. Oh, yes, I guess you're right. Yes. It's really the same number of molecules, right? At a lower speed, but the same area. Yes. You could do that. Sure. Lots of ways you can answer that. It's the same number of molecules, right? But a higher proportion at a lower speed. Surface area has to be constant, right? The surface area is constant. So that is why B is up and to the left. That's why B is up and to the left. I guess higher and to the left. Questions so far? Take a look at the packet. Take a look at the higher, lower, or just leave it? Okay. So the packet kind of summarizes everything we've talked about the last 2 days. So if you want to see what we're going to be doing this year, you can go over there to the CED. So that is the course exam description over on the left, if you've ever seen that big chart over there. At this point, we have covered pretty much all of Unit 1. And we are into Unit 3 now. We're going to come back for Unit 2 in a second. We've also covered the majority of Unit 4, because listen to this. Reactions, net ionic equations, representation of reactions, stoichiometry, introduction to titration, types of reactions. Do these sound familiar? Redox. So, I don't teach it in the order that they want you to because it doesn't make sense. Makes more sense to do it the way I'm doing it. Also, it goes along with our book, which is also kind of nice. Okay. Can I move this? All right. So this packet, this is a really good summary over what we've talked about. During COVID, this was called an I do, you do, we do, and I was able to help with some of these. So what it basically was kind of notes. You would work it out, and you could like practice it on your own. You could scan a QR code and like watch the video. It was actually kind of cool. But here's some particles moving at a speed. Flip the page. We're going to talk about these gas laws starting tomorrow. You guys have heard of those before. Boyle's law, Charles' law, Gay-Lussac, Avogadro. And then here is the Maxwell-Boltzman distribution. All right? So, this is what we were talking about today. And this is just kind of like a study tool for you to read through. Flip the page. So, we've got gas A, gas B, right? Which gas is at a higher temperature? Gas A, right? Why? More lines, right? Yes. Gas A, gas B. On this one, now how do you know though? Because these particles are what? The same mass, right? It has to be a constant mass just to be able to compare their speeds. Now in this example, the mass of the particles differ, but the velocity is the same. Right? So which one would have the higher kinetic energy here? B, right? Because if Ke equals 0.5 mv squared, yes? And their speeds are the same, then the larger particle is going to have more energy. Head nod if that makes sense. Okay, cool. And these are just things I can't draw very well. So that gets us down here into our rate of diffusion. We talked about this 2 days ago on Friday. So the ability to diffuse through a small hole, we talked about that, right? Yes? I gave you this equation. We used to do a lab like this, but we don't have time anymore. So we would put a cotton thread, like a Q-tip of hydrochloric acid in one end, and a Q-tip of sodium hydroxide on the other end, and it would form a little smoke ring in the middle. And then you calculate it, but for one equation, it just kind of was. Yeah. Okay. I try to do labs that aren't meh. If they're just simple, like, why are we doing it? Okay, so here we go. Given a sample of hydrogen gas, hydrochloric acid, and chlorine gas at the same temperature, place the particles in order of decreasing average speed. So, key word here is at the same temperature. At the same temperature. So at the same temperature, the fastest is going to be H2. Why? It's the lightest. It's the lightest. The slowest is going to be Cl2 because it's the heaviest, and hydrochloric acid is in the middle. Now we're talking about HCl as a gas, right? Which is not great. It's not great. I've breathed it in. It's horrible, actually. It'll kind of, take the coating off your lungs. If you were, for say, mixing up hydrochloric acid and forgot to turn the hood on. Yeah, I'm not saying I've ever done that, but it'll clear the sinuses, for sure. So, here we go. Consider an equal molar mixture of gases, H2, N2, F2, placed in a container with a pinhole opening. After some time has passed, place the gases in order of increasing amount remaining in the container. So do that. Increasing amount remaining in the container. So try that on your own. No, we're not going to do that. Because we're here. Left to right. So of increasing amount remaining in the container. So the least on the left, the most left in the balloon. I imagine this as a balloon. I don't know why. On the right.
Oh,
Helium's not diatomic.
No,
Hydrogen is.
we never really talked about the noble gases.
We're going to talk about the noble gases this year. Yes. They're weird. They're stable, but they're weird. They can do some weird stuff, especially xenon and krypton.
One of the book problems has xenon and then like you had to like assign an oxidation state. That was annoying.
But you could do that. Was it just xenon by itself?
No, it was xenon and a compound.
Okay.
Like two of them.
Least amount would be what? H2, because it's the lightest, so it's going to get out that hole quicker, right? Yes? Diffuse more quickly. Next one's going to be N2, and the last one's going to be F2. So you're going to have the most fluorine gas left in your balloon. A vessel containing 1 mole of H2 at 200 Kelvin is shown below. Draw the following. So take a second and draw these 4 scenarios. Make sure you are following, well, it doesn't really matter. It tells you what to do. But remember that this is 1 mole of H2. 1 mole. Follow the law of conservation of matter. Diagram drawings. You're going to have to do one on the AP test, I guarantee you. Also, you're going to be kind of upset when you see the diagram from yesterday's test. I don't think anybody got it. Maybe one. It was actually super easy. Also, there's a typo on this page. If you find it, I'll give you a piece of candy. But do this first. Now everyone just wants candy. No. That's not it. I mean, you might be right, but that's not the one I was thinking. You're probably right, Jolly. How many more do you have? 1 more minute? 2 more minutes? Huh? No. Noble gases are perfect. They exist as single atoms. Okay, first one. 2 moles of H2. What are you going to draw first of all? How many? 6. 1, 2, 3, 4, 5, 6. How should my arrows here be compared to here? About the same, right? And like, you're not going to be drawing arrows on the AP test, right? Because how would you be able to grade that? Yeah, we don't have time for that because they scan it in and we grade it on the screen. So there'd be no way to do that. A 1 liter vessel containing 1 mole of neon at 200 Kelvin. What are you going to draw here? 3, but what's their size going to be? Larger. So you need 3 larger molecules still moving at about the same speed as the first picture. A 1 liter vessel containing 1 mole of H2 at 100 Kelvin. So how am I going to draw this one? 3 pairs with shorter arrows, right? So 3 pairs with shorter arrows. And then 1 liter vessel containing 2 moles of H2. So I'm back up to my 6 pairs, right? 3, 4, 5, 6 at 400. So I have to draw these arrows a lot longer. Ooh, look at this. Mine are even bouncing off the side. All right, that's some fancy arrows. So moving more quickly. Number 2, equimolar samples of N2 and O2 are both at standard conditions. 1 ATM, 298 Kelvin. There was the mistake. So fix that. Fix that. Which sample has the most kinetic energy?
O2.
And
That's greater mass.
beep.
Okay.
Oh, wait. Equal molar samples.
So it was like 1 mole.
Wait, so if they're... Wait, it's not equal. Wait, it's equal molar... Okay, but you have to why.
So you said it's not as
So we're assuming they both have the same molar mass.
They have the same amount.
Oh, they're the same.
It's the same. Because kinetic energy is the what?
Mass.
Average.
The average, right. If they're both at the same what? Temperature. Temperature is the measure of the average kinetic energy. So if they're at the same temperature, it's going to have to be same.
Even though the 6.5 and squared, that's not.
Well, that's going to be the second part. All right? Same temp equals the same average kinetic energy. Now, on the second one, if I ask you which sample has a higher average molecular speed, what would you say?
It would be...
N2. Why? Yes, you got it. So, don't get kinetic energy confused with molecular speed. Flip it. Place the following gases order of increasing kinetic energy. Try number 3.
We were good bad handwriting on the AP exams, like so bad you can't read it.
Yes. That happened once to me. I graded like 5,000 papers. There was one where I had to escalate it to my table reader. So the way it works is there's a table of 8 people. We're all grading a question.
You get the same order.
The same one all week. So I grade the question, and then my table leader back reads me. So they are scoring some of the papers I grade to make sure it's the same. And then the table leader is being back read by the question leader. So then there's several of us grading one question. There's a question leader. So the question leader is back reading the table leader. Then the question leader is being back read by the exam leader, who's grading all of those too. So like some tests are graded 4 or 5 times to make sure it's accurate on the rubric.
How is seniority determined amongst the graders?
Good question. So you started out a reader, right? Your next step up would be to become a table leader. But here's the thing. So right now I have kids. And for me to go out there, it's a total of 9 days. With the flying out there, 7 days of grading and flying back. Long time for me to be away, but I'm getting paid. If you want to be a table leader or a question, anything above that, you have to come out for the pre-reading. And then the pre-reading, you're grading thousands of exams and 2 or 3 days before that to come up with your example papers of like, what's a 2, what's a 3, what's a 4, what's a 5 for each question. And then all the little nuances that you might see. So if I wanted to move up, I would be gone for 2 full weeks of my summer. So maybe later in my life. But right now I'm good with like, but the cool thing is, Dr. Bonvalet, anyone know Violet or Nathan?
Yeah.
So he was the chief reader. So he wrote the exam. So he was the head person in charge of writing the exam, grading it, in charge of it for several years. He's a professor at the College of Worcester. He is going to come in and train us like we are readers in the spring. So that will give you a really cool perspective on what does it look like, what are they expecting, and like I could do it, but it's cooler to have him do it because you see me every day. So, anyway, I've never met Dr. Bonvalet. He's hilarious. Oh, okay. Yeah. Oh, yeah. You guys live over in that circle, right? Yeah. He's really cool. He's got the dad jokes, too. All right. What'd you say for the least? C. Next one, A. Next one, B. Ah. Well, all right. Now, draw your new curve for each one of these. So for A, gas is heated. B, maybe do it in pencil in case you have to erase. But I think you can get it right the first time. You can do this. If you can do this, this is the main thing you have to do on the test with the Maxwell Boltzman distribution.
Some gas was removed from the vessel.
Figure it out. You can figure that out. Trying to find different resources that are helpful.
I'm trying to make this like
Maggie, look at what I did today.
I was very worried about you during that exam.
I was worried about myself.
Guess what I'm doing in honors physical science today? Gas laws. We're almost in the same stuff.
I'm sure.
All right, you guys got it? First one heats up. How's it going to look?
To the right.
And lower. Right, so it has to be lower and to the right.
I do it in the wrong place. No.
Second one, higher molar mass at the same temperature.
That means we're moving slower, right?
If it's a higher molar mass at the same temperature, it's going to be moving slower, which means a lower temperature. So my hump has to be higher to the left. Higher to the left. Does that make sense? Jack, you good?
no, but I'll really watch it and figure it out.
But let's just talk about it though. All right? A higher molar mass at the same temperature. So if two things are at the same temperature, right? And one is heavier, right? That molecule is going to have a harder time moving as quickly. So it's not colder, right? But the speed is going to be lower. We're talking about molecular speed here. Talking about molecular speed.
Okay.
This one, some gas was removed, temperature held constant. Same hump but smaller. Same hump but smaller. Because I'm going to have less area,
Yes.
less
So
particles.
because there's the amount of gas is different, the areas under those two are not going to be the same.
Well, correct. So now my area is changing. Would I be able to change two things on this? Would I be able to change my area and the temperature? No, there'd be no way to draw that, right? There'd be no way to change the temperature and the amount. So you have to keep something constant in order to change it. And then the last one, a hotter gas was added to the original gas and allowed to reach equilibrium. How would you draw this one?
To the right.
How?
A little bit shorter.
Higher and to the right. All right?
What is the phrase equilibrium? Like, what does that mean?
Equilibrium, not super important yet. All right? Because I added gas.
Yeah, but if you
I added particles, so then my hump is going to be higher. I added more to it. More area.
Shouldn't not making it higher, if you made it the same height but made it to the right, shouldn't that make it have more area? Because for the first one, that has the same area, but it's shorter. So the second one, even if you didn't make it higher, shouldn't that still have the same area?
But on this thing, I'm changing two things at once. I'm changing the temperature and the number of particles, so it has to be higher to the right. Has to look like that.
For number A, we did,
If I was only changing one thing, Jawa, you'd be right, but I'm changing two here.
for A, we did change the amount of gas in the container.
Changing two. Okay. Number 5. 2 gases are placed. This is in the lab that I said we did, but like you can literally figure this out in 1 second.
Okay, we need
Where would draw a line where you would see the ring if these 2 gases were put in a tube? So draw a line where these 2 gases, where would the line form to precipitate, form in the tube? Draw that on here where you think that would form. I like that you're looking at the periodic table.
The blue one? The one below chlorine?
It's third column below.
The one next to it.
And on the other side is selenium.
The one that says BR.
HBR's greater than Maxwell is just like slower. So it's gonna be right there.
Yeah!
Jack, where'd you draw it?
Okay, so if like middle's here, we're gonna go this way.
Closer to HBR. It has to be closer to HBR. Why?
Because HBR has more mass.
HBR is heavier. So your NH3 is going to be able to move farther across the tube than the HBR is. Last one. A sample of nitrogen monoxide was placed in a sealed rigid container at 200 Kelvin. The vessel was heated to 400 Kelvin. What changes will occur and why? Consider changes to volume, temperature, pressure, moles, and particle speed.
Change the amount of moles from that.
Well, let's see. Let's talk about volume first. What's going to happen to the volume?
It's gonna expand. Wait, it's in a sealed.
Sealed rigid container. Same. Temperature. Why?
The heat is 400 Kelvin.
Yeah, exactly. Pressure. Why? Because I have more what? Collisions, right? More collisions. Number of moles. Same. Why? Did I change my number of particles of gas? No, I did not. And then lastly, particle speed is going to increase. Because we know that speed and temperature are directly related. Okay.